and I, UIT and I started to think about maybe can we, update MCMC in such a way that it will actually give you reasonable answers after a finite amount of time if you have a very large data set. And we were inspired by gradient ascent, which is basically you take your prior plus your likelihood term, which is proportional to your posterior, and you compute a gradient with respect to your parameters, right? So that decomposes into these two terms. Now this is the offending term because it depends on all the data set, right? And you take a gradient step. So people have known how to deal with the big data problem for learning, for gradient descent learning. They just do stochastic mini batching. So they, instead of for every update, you look at all the data, you look at a random subset of the data, and then you scale this thing up by a factor n over n, so that so you get sort of updates the infinite amount of time. And of course, there's a bunch of requirements on that epsilon, the step size. The step size has to decrease over time and satisfy these sort of constraints. So that's just stochastic gradient descent that we all know and love for deep learning, works very well. But then there's this other algorithm called Langevin dynamics, which is really just like gradient ascent. But then if you miraculously add like this noise term, it's a normal distribution with zero mean and epsilon. Now note epsilon is actually the step size, or 2 times the step size. So if you add this amount of noise to every step, then in the limit of very small epsilon, you will sample from the posterior distribution. So instead of actually converging to a point, you'll be sampling from the correct posterior distribution. It sounds like a miracle, but it works. And then since we cannot actually do very small epsilon, what we do is we add a Metropolis Hastings accept reject step to make sure that we actually sample from the correct distribution. Okay, so that's called Langevin dynamics. And then we thought, well, there is a very close parallel between these two. So let's see if we can also make a close parallel between these two. So now instead of looking at all the samples, we draw a small subset of the samples here. So we scale by the factor n over n. And we have also a step size which is decreasing over time with the same requirements. And since this is a very expensive step as well, it looks at all the data point, we just remove it and observe that if epsilon goes to 0, in fact, the procedure will sample from the correct distribution. And so this then is stochastic gradient Langevin dynamics. It's the first of a long list of algorithms which improved this particular algorithm, which runs MCMC when you have a very large data set and gives you approximations. And so what have we really done? So as I said, in variational Bayes and MCMC, one has sort of a bias. The error is represented by a bias, and the other one has an error that's represented by the variance. So we play the same game here. So on the one end, if you have a distribution with a large step size, then you're sampling from the wrong distribution, but you're making a lot of progress. And because you're making a lot of progress, you can draw a lot of samples. And so the situation is you're drawing from the wrong distribution, but you can draw many samples. So this means that you can reduce the variance in your estimate, but you increase the bias in your estimate. And in the other limit, when epsilon is very small, you will only draw very few samples, or independent samples if you want, but you're drawing it from a distribution that's closer to the true distribution. So all this is doing is basically sort of playing this game of bias, variance, error, just putting the error either in the bias or the variance, and it turns out it's actually beneficial to trade off a little bit of the variance with some of the bias. And so in variational Bayesian learning, so the situation is a little bit different. So again, we're in a family and we're trying to find the distribution which is closest to the true posterior distribution. So now let's look at that free energy equation that we have. So again, that's an integral over the approximate posterior times the log of the likelihood in the prior, and then this entropy term. And then in order to maximize this, the best way to do that is to actually do a reparameterization. So this is something that Dirk Kingman and I introduced in 2013. So instead of trying to do this complicated integral, which might still be complicated even though Q might be a simple distribution, what you do is you transform theta to another variable omega, random variable omega, and this function going from omega and phi, maps these to theta in such a way that this measure q theta d theta equals to p0 omega d omega. And then the important part is that this distribution should be a standard distribution, a distribution that does not depend on any parameters. It could be like a standard normal distribution, doesn't depend on any parameters. The parameters are now in this function. So if you then apply that transformation, then this q turns, d theta, q theta turns into d omega, p0 omega. And then every time you see a theta here, you have to replace it by this function f omega phi everywhere. Right? But now, and then you have to, and now you can turn the gradient, you can pull it through this expectation, and you can apply it here and here and there and there. Okay, so that's called the reparameterization trick. And in fact, this is a really important trick because it reduces the variance. If you would start sampling from this distribution directly and use an algorithm called reinforce, you'll have very high variance, and this trick will reduce the variance a lot. So that's the way that we can train these variational Bayesian methods efficiently. Okay, so this is the introductory part. Now I'll tell you a little bit about efficient deep learning. And so I just want to share with you this plot which I made, and you should take with a lot of grains of salt, because I just looked up some models in the literature, and I just, hypothesized that the first models in 1943, which were the first sort of perceptrons, they could have ordered 10 parameters because there was not really a computer to learn them, so you may have to have set them by hand. So let's say that in 43, there were about 10 parameters in our models. And then in 88, which is the sort of previous neural network hype, there was a model called NetTalk, which had about 20,000 parameters, which seems a lot at that time. And then in 2009, when Hinton started his deep belief net papers, there were about 10 million parameters in these models, which at the time looked like incredible. And then I visited Google and Yahoo actually in 2013, and people were talking about models with 1 billion parameters. And nowadays, when you talk to people from Google, they apologize if they say that their model is only 1 billion parameters. And then, oh God, what is that? All right. And then in 2017, there was a paper called Extremely Large Neural Networks, which had 137 billion parameters. Right? And then if you plot these numbers like on a log linear plot, which basically means that a straight line is exponential growth, you'll find that if we keep on going, then in 2025, we're going to reach 100 trillion parameters, which is about the size of the brain, if you want. That's the amount of synapses we have in the brain, right? And that's not very far away. I mean, we all hope to live, to that time, which is interesting, right? It also points to the fact that these models, as they grow, they're using more and more energy to run, and the question is, is this a sustainable path forward? And I'll argue that there's multiple reasons why this is not really a sustainable path forward. And maybe we can be a bit inspired by the human brain, which seems to do at least 100 times better in terms of energy efficiency. Okay, so why do I think that it is important to start dealing with this energy question now? I think there's two really important reasons. The first one is that the value created by AI must in fact exceed the cost to run the service, right? So if you rank posts on Facebook or other social media, right, and you're going to spend a little bit of money, maybe in the order of a 10,000th of a cent, a microdollar, let's say, on each one of those rankings, then the revenue you get by doing that in terms of advertisements should outstrip that money that you invest in running that that neural net, right? And as we start to run these models in sort of bigger and bigger environments, at some point the economic benefit will outweigh, the energy cost will outweigh the economic benefit. Now, there's another reason why, energy efficiency is really important, and that's that I believe that a lot of the AI will move from the cloud to the edge, right? And so if you have like a smart hearing aid, you don't want that hearing aid to use a lot of energy. First of all, there might not be a big battery in that thing, but also you don't want it to warm up a lot, behind your ear. Same thing with a cell phone, where it shouldn't sort of get very hot in your pocket, right? So when we are applying these methods to edge computation, it's really important that we make sure that the energy envelope is under control. So the workloads are very compute intensive on phones. There's lots of complex concurrencies. You have to do many tasks at the same time. Often it has to be done in real time, and it's always on. At the same time, of course, you have really a small device. You don't have a lot of storage, and you don't have a lot of battery life. So that causes really a lot of sort of challenges, and sort of energy consumption is a big issue. So therefore, the central sort of statement I want to make here is that maybe we should start thinking about AI algorithms and measure their success not just solely in terms of their accuracy, but in the amount of sort of intelligence that they provide per kilowatt hour, right? So how much intelligence can we extract from a neural net, per joule or per kilowatt hour? Okay, so now I'm going to try to go into a little bit more detail about some things. So here's a neural net, and I'm going to, sort of explain to you first the local reparameterization trick, which was introduced in this paper here, where what you do is you convert the stochasticity on your parameters to stochasticity on your sort of neurons here. So basically, in equations, when you look at the energy term of the free energy, it's an expectation over theta py given sort of, and then theta times the nonlinearity times the previous activations. So we're going to convert that into a distribution over the activations z given the previous activations, and then py given z, because that's this term, right? And so in an animation, this looks like this. So you can see these things wiggle here. So this is the parameters which are being fluctuated under the prior or the posterior, and that is converted into sort of fluctuations on the activation. So that's sort of an animation of what the local reparameterization trick really does. And now I'm going to try to explain to you how that idea can be used to remove, or how Bayesian statistics can be used to reduce energy in neural networks. Okay, so we start with a model that hasn't seen any data whatsoever, and we're going to look at these two parameters, W1 and W2. So they're on these axes here, so W1 value, W2 value. Right? And now we're going to use this sort of wiggling so that we wiggle the whole thing. So the whole method is stochastic, right? We have a posterior distribution over our parameters, and the whole thing is stochastic. And as we wiggle this thing, these parameters W and W2, they take on different values. Right? So this only happens in a Bayesian perspective of deep learning. And then, okay, so this is under the prior, wiggling under the prior. Now we're going to use data, and what's happening is that we're going to change this prior distribution in a posterior distribution over possible values. Right? And what we see here is that the W1 actually was constrained to a small value. So we really transformed the data into parameter values, right? So we moved the information which was in the data into the value of parameter W1. But W2 actually, wasn't constrained at all. It stayed equally uncertain. And so that's sort of like a very useless parameter. And now what I'm going to say is that we can either remove that parameter, or we can quantize it so that we can represent it at very low precision, right? And if we represent it at very low precision, you can potentially run it at much lower energy cost on hardware. And somewhat a similar procedure happens when you actually look at the values of the activations, and some of these activations remain completely uncertain and quite useless, and some of these neurons can therefore be pruned using the same ideas. Okay, so now I'll go into more detail, explaining a little bit about recent work on using Bayesian statistics to do compression. So in terms of the equations that are already explained, we need to choose a prior, in this case a prior over the parameters, and we use this auxiliary variable z as well, which we integrate over, to define a prior over the weights. And the thing that you really need to sort of take away from this prior without trying to parse this equation too much is that it's a very sparsity-inducing prior. It really likes things which are not very useful to go away, and it's a sparsity-inducing on the level of the neurons, not so much on the level of the parameter. So it's trying to get rid of entire neurons if they're not contributing very much to the prediction. We also have to choose a posterior distribution, Q of W comma Z, and this is the particular version that we use. It's called a dropout posterior. This paper by Dmitry Vetrov and his students developed it, and we have also some work that's closely related. So the posterior is the important part of this is that the mean and the variance are proportional. So bigger means also have larger noise. And so if you encode this in this posterior distribution, and then, so this is a very beautiful animation that was made by Dmitry Vetrov's students, where you show, if you run this algorithm, if you do inference and learning in this algorithm, how this method sparsifies. It just gets rid of most of the parameters of this model. So here you see the accuracy. The accuracy stays about the same. So you're not actually compromising the model in terms of its accuracy. But the compression ratio goes up to 270 times, which means you just keep 1 out of 270 weights. The rest all go away, right? And it completely sparsifies these filter maps. So this is really fascinating, in my opinion, that we over-parameterize these neural networks by such a large degree. And I've learned, throughout this conference, actually, that this might have a lot to do with the fact that you can do a lot better optimization if you're in a much bigger space. But then once you have found your model, you can then prune it down very effectively. And clearly, once you've pruned it down, many of these filter maps can just be thrown out, and that will help you save energy when you do the computation. So here's the same plot, but now for the last fully connected layer, and you see that almost no weight survives, and the compression and the accuracy just stay the same. So I think this is a very interesting result where we can use Bayesian methods to compress these models by a huge factor. So I want to go a little bit into, in the last 10 minutes, I want to go a little bit into some of the more recent papers that we did. They're not even published. They're somewhere out in the archive, probably. So this is work between OpenAI and MLAB, where we basically, again, look at the the energy term, and we write every parameter as a theta prime times a function g of s, which which basically you can think of it as either a soft version of a binary value 0 or 1. So if it's 0, this parameter prunes out. If it's 1, it will keep the parameter in. But the point is we're actually making it a soft version of it. So in fact, the version is called hard concrete. So the model is like this is the distribution. So it has a little bit of probability between 0 and 1, but it has a spike at 1 and it has a spike at 0. And then we add an extra term which basically says the probability for non-zero values of this function should be restricted. I want most of my mass to be on 0 so that I can prune out as much parameters as possible. Okay, so there's some results that again you can keep the same accuracy, but you can reduce these models. So this is the MLP with 784, 300, and 100 neurons, and you can get down to 219 to 1400 or 266, 88, 33. So there's a huge amount of compression that's happening if you apply this, and this is a fairly practical method, I would say. So this is in other work. This is with Bosch-Juva Delta Lab, which is a lab within the University of Amsterdam. Sort of Jorn Peters did this work. And so this is a binary neural net. Again, I'm going to exploit the fact that we are going to use stochasticity and probabilities in order to run it at higher efficiency. So there's a distribution over, the model parameters here. Because of central limit theorem, you're collecting a lot of these sort of binary values. You get some kind of thing that looks like a Gaussian distribution here. Then we define stochastic batch normalization and stochastic max pooling, which are generalizations of batch normalization and pooling for the case of stochastic random variables. Then we threshold again. So we take this distribution and we threshold it at some point. So again, we convert to a binomial distribution. Then we sample from that. And then we have, again, the next layer of binary activations. And then it turns out you can do backpropagation throughout this whole chain. And you can train these networks quite efficiently and get fairly good results. So here's another piece of work between Qualcomm AI Research and CUVA, where again, we think about training a neural net, knowing that in the end, the parameters will have to be quantized on a grid. So that we are going to train it so that it knows that it's going to be quantized, and it doesn't lose a lot of accuracy when that happens. So here is sort of the values for the parameters, and we choose some grid points. In fact, you can also learn the grid points. We have some distribution over where the parameters can land, and then we have a probability. So we basically throw all the probability mass here. We throw it sort of in this bucket, and this becomes this probability. And since this is all done with probabilities, you can actually train and backpropagate through all these probabilities. And you see after training that the model really likes to quantize itself. It likes to sort of put spikes on these sort of grid points. And in fact, the last layer, it tries to binarize itself. So again, you can sort of train yourself to be quantizable, and the results look pretty good. OK, so the last topic I want to talk about is spiking neural nets. So this is another way in which we are wasting a lot of energy. If you have like a surveillance camera, it's looking, at a shop. It's really 99% of the time nothing happens. And so if you would analyze every frame using a deep neural net, you're wasting a huge amount of energy, right? And so it's basically like this, which is a sort of a spiking camera, which only processes things that change. So that sort of inspired us to come up with a spiking neural net. So the normal neural net has an input, then has a linearity, then has a nonlinearity, etc. So we replace that by an input. We do an encoding step. I'll explain a bit what that is later. Then we do a quantization step. Then we do a linearity, and then we do a decoding step. Okay, and so the input is the encoder is now a stateful sort of representation. It's a linear combination of the actual signal that's coming in and the difference with the last signal, right? And this is basically the fact that you look at the difference. If nothing changes, then this term goes to 0. So then the quantization is known as something like sigma delta modulation, and it's similar to something I did a long time ago called herding. I knew it was good for something, and we found that it is good for sort of quantizing these input values. It's basically a little potential that rises, and then you sort of, when it reaches a certain point, it sends out a spike, and then it sort of resets. And then this is the inverse of that, so it's sort of the decoder. And what happens if you only take sort of differences, or the sigma delta modulation in its pure form, if you have a signal, it's going to approximate that signal by a piecewise constant function. And every time it sends a spike, it changes that level. And if we do this thing, if we add a little bit of the input, it will have exponential decaying sort of parts of it as well. And so the most important thing is we have to mix this in so we can actually do stable backpropagation on this spiking neural net. And again, so this trains very well. OK, so let me quickly then sort of stop. We've discussed black holes and physics and how it relates. Really underlying all of that is information theory. We've seen that gravity might actually be entropy maximization. And from the Hitchhiker's Guide to the Galaxy, actually, we know that the Earth really is a big computer that is trying to compute the answer to the ultimate question of life, the universe, and everything, and it's built by these mice. And if you think that's funny, let me remind you that there is a bunch of people who actually do think that we live in a giant simulation. And so maybe it isn't all that strange of an idea. In fact, if you look at this, in some sense, you could argue the universe is a huge computer trying to compute something. So we looked at basically the free energy cycle, going from physical free energy to model free energy and back. I've talked about Bayesian deep learning and how it can help us compress and quantize our neural nets in order to save energy. Of course, we all know that Bayesian methods also help you regularize and generalize better. There's interesting work also here at ICML on using Bayesian deep learning for confidence estimation. And finally, there's also interesting work that shows that Bayesian methods can help you train more privacy-preserving models. And also, it seems to give you a little bit of robustness to adversarial examples, but it doesn't protect you completely. OK, then let me end by this quote, which surprised me, that Steve Jobs actually knew about free energies. It says, this revolution, the information revolution, is a revolution of free energy as well, but of another kind, free intellectual energy. So I would say think deep and think free. And then I have two quick announcements. We have recently started Qualcomm AI Research, which is an environment where we can do fundamental research and write papers about all of these intriguing problems about compression and quantization. And of course, we are hiring like everybody else. Actually, we are also hiring at the University of Amsterdam. We are looking for a chair in machine learning, full professor. So if you're interested in that, let me know. And then this is the final slide, which happens to be slide 42, also written in 42-point calibre light. And so if you have any questions, then you know what the answer is going to be. Thank you very much.
So thank you, Max. Are there questions? Yes. Can you go to the mic? So.
There's somebody there, too.
Thanks for the talk. I'm Irgolami from Berkeley. Could you please comment, you mentioned compression using Bayesian inference. Could you please compare how this compares with the state-of-the-art compression methods? You showed 240x compression, but that was for a very simple problem for MNIST, which we know that's not a very representative problem in deep learning.
Yeah, so of course we did a lot of experiments and a lot of other data models as well. And we compared to a number of other methods, including sort of more SVD, sort of SVD type models where you sort of constrain the weight matrix and clustering methods. And it typically looks like for large compression values, it does a bit better than if you would use these other methods. And for smaller compression levels, it would do about the same. But you should read our papers to see the full story about that, because we have lots of experiments where we do all these things.
Misha Chertkov, Los Alamos. So Max, you started by saying that physics is information, and then you discussed how you reduce number of degrees of freedom in deep learning. But another approach would be to put physics into those models. We often model physical world or engineering world. So can you comment on that? Another way to reduce.
So that's an interesting suggestion. So one way I could see that could happen is if you, and that's something that we are definitely doing, which is you can model the device on which you are doing your computation. I'm not sure this is what you're heading for, but so if you model, your phone or whatever you want to run your deep learning model on, then you can sort of directly optimize against that simulation of that device or the real device. So in other words, you use the physics to evaluate how well you're doing, and you give feedback to the learning algorithm to optimize against it. Is that where you're heading at, or maybe a more fundamental?
Well, I guess I'm asking how we mix physics of phenomena we want to model with deep learning per se. So physics and form type of learning.
Yeah, we'd have to think about that more. That's a difficult question to do here on stage, but we should talk more.
Okay. Yes?
Thank you for a very nice talk. I was wondering, when you compress these neural networks, of course, you're making them simpler. Does it also mean that it makes it easier to explain what they're doing, either for a decision or to extract insights into what the network has learned that can teach us something?
I wish that were true, but I don't think it is really true. So it's just removing, bits and pieces of the model. So it's just, removing sort of filters, and it's removing weights. It's quantizing weights. So I don't think when I look at that, it looks any more interpretable to me than it was before, unfortunately.
Thank you.
Yeah?
Thank you, Max, for the talk. One question I had is, while this method is, this whole philosophy is striving for intelligence per kilowatt hour at the prediction time or consumption time, there's also the same question at the training time.
Yeah.
So right now in the current way of doing things, we are absolutely ignoring efficiency during training time, justifying for optimization of whatever we are seeing currently, and then focusing it on the downstream. How do you see this paradox or this paradox resolve?
Well, it's a good question. And in fact, fortunately, you often have to do training once, or not very frequently. But execution, you may have to do like 1 trillion times a day or something like that. So there is a big difference between those two things. Yet, I think it is very interesting to think about if you can also improve the efficiency of training. So typically, many methods, they use full precision representations of the model during training. And then, but you could imagine that you could develop methods that already use low precision, let's say, weights and activations during training time as well. But I think that's a wide open area that looks very interesting to me.
Okay. Next question. Yeah.
You mentioned Maxwell's demon. So I'm wondering if you're familiar with the arguments for reversible computing and how you view those arguments.
Yeah, so interestingly, so at the very last part of the resolution of Maxwell's demon is that when you do reversible computation, so it turns out you can do these measurements of where all the molecules are during reversible computation, so that doesn't cost you any energy. But it seems that, if you're at least thinking of a cycle, that at some point you'll have to delete some of the information that you've written down. And it's this deletion process which is not reversible, clearly. And that's where you're going to spend your energy. So it turns out that any reversible computation can be done at 0 energy cost. But typically, there is parts where things are non-reversible, and that part is what you're going to cost you energy.
Next one.
Thanks for the great talk. So I find the spike neural net quite interesting. So a general question is about, have you thought about using the spikes to code the gradient? Which means, in other words, your gradient stays at 0 most of the time, but when you want to move, when you're very sure which direction to move, you give it a big spike. So the temporal average of the spikes basically encode the temporal average of the true gradient. I was wondering whether that's related somehow in concept.
Yeah, I think I have to think a bit more about that, but we actually, in our backpropagation pass, we also use a spiking architecture. So both the forward and the backward pass is using spiking, but then we do collect statistics before we actually do an update. So maybe you're suggesting something that even goes further, which is also encode the actual gradient in terms of spikes, but we haven't thought about that. We did think a little bit about if you have multiple sort of agents and they're sort of distributively learning, whether the messages between sort of the distributed learning agents can be represented using spikes. But it's a bit different than what you suggest, which is interesting.
Okay, thank you.
So we'll take the last 2 questions, and while doing that, can we have the next speakers start to set up?
So thanks for the talk, which is I see it as all about how physics and computation are intertwined at a deep level.
Yeah.
And your background is in physics, and you know, so we could think that it was that background enabled you to see these links as you moved from one field to the other, or did both of them. But you could also see that or see it as your background in physics caused you to you know, just really love the possibility of such connections. So I just wonder, you know, as you look at your own self and introspect, do you see both these forces, and how do they interplay?
That's a personal question, very interesting. Yeah, surely I love the sort of the fundamental nature of those questions. And maybe I was speculating a bit in certain ways, but I actually like to think that, you know, sticking out your neck and speculating a little bit is not a bad thing. But yeah, I guess it has influenced me a little bit in the way to think about this, yes.
Thank you.
Hi, Max. Thanks for the talk. I'm wrangling my brain now to try and figure out if there's a connection between the adversarial problems that these networks face and entropy, and if there's a connection between this compression as a way of helping to battle the adversarial example problem.
You mean like how Bayesian, or how, if you quantize a network or compress it, whether it will help you against adversarial examples?
Right, so somehow you're in some way reducing the dimensionality of the network a little bit,
yeah.
Even though you're getting rid of extraneous information in there. But maybe
Yeah, so
this
I think
is a way to, yeah, exactly.
I think I don't want to make any claims here, because it seems like any time somebody comes up with an adversarial sort of, you know, protections, you know, it's easy to beat it again. There is some papers that say that at least following a Bayesian perspective will protect you a little bit, but not completely. When you're doing massive compression of your neural net, I don't think we can actually say with any certainty that it will become more robust against adversarial examples, or less. So I don't think there's a clear connection, but maybe, who knows.
Okay, thanks.
Thanks.
Thanks, Max. Let's give him a round of applause again. So our second talk for the plenary session is another Best Paper Award. And this is a Best Paper Award for Delayed Impact of Fair Machine Learning by Lydia Liu, Sarah Dean, Esther Rolfe, Max Simkovich, and Moritz Hart. Let's give them a big hand of applause.
Hi, everyone. Thank you for coming. So I'm going to speak to you about the delayed impact of fair machine learning. This joint work with my co-authors, whom has already been introduced. So I want to first start by sharing with you a cartoon about fairness research in machine learning. So there is a clear trend in our field, which is that it's an increasing trend. So the number of papers that's been written about fairness has increased exponentially, and up to last year, and this is our projection for, say, 2018. And it is very encouraging and exciting that fairness has become an active research area in our community. And a lot of this work has focused on different mathematical definitions of fairness and how we can achieve these algorithmically. So earlier this year, Arvind Narayanan had a tutorial where he confirmed there exists at least 21 different definitions of fairness. So one question now is, what do all these criteria do? So in fairness research, there is a notion of a protected group defined on the basis of a sensitive attribute, which could be gender or race, for example. And there's, in a lot of work on algorithmic fairness, there tends to be an implicit assumption that fairness criteria will make the protected groups better off, or at least protect the protected group from some kind of harmful outcome. But the justification for this is often left to intuition. And in our work, we critically examine if this implication is actually the case. So let's first explore this question with an example. So here I'm showing you two groups, a blue group and an orange group, and which could stand in for two different race, gender, or age groups. And these are the histograms of credit scores in each group. So higher credit scores implies a greater proportion of people repay their loans. So here, the solid circle indicate the proportion of people who would repay, and the empty circles indicate the proportion of people who would not repay. And a priori, we do not know who would or would not repay their loans. We only know at each credit score what is the proportion of people who would and would not repay. So now, given these scores, the bank would like to know how do you give out loans to these two groups. And if they care about fairness, say for example, we could think of the blue group here as the protected group, and we want to apply some fairness criteria to ensure that the loan policy is fair in some sense. So let's try applying one of the common fairness criteria called demographic parity. So what does that mean? It means that we have to approve the same fraction of loans in both groups. This translates into having two group threshold scores, and we only approve the loans if the scores are above the respective black thresholds. And now with this policy, you are approving the same fraction of loans in both groups. So now, after an individual gets a loan, the scores will change as a result of whether they repay or default. So for example, in the orange group, we can see that all the people who got loans actually repaid their loans, and their credit scores went up as a result. Whereas in the blue group, more people defaulted than they repaid, and on average, the score of the group actually got worse. So why is this a problem? So having, if your average group score goes down, that is a harm, because on average, that means you have more debt and less access to credit in the future. So it's definitely an undesirable outcome. And so what I've shown you with this example, right, is that once we applied fairness criteria, it did not seem to help the protected group, especially if we consider the impact that loans have on scores. So this really motivates us to study more systematically the delayed impact of classification. So what we did in our work, first we introduce a tool called the outcome curve that allows us to compare the delayed impact of fairness criteria. And so this is what we did just now in that simple example, but in a much more systematic manner. And we also provide a complete characterization of the delayed impact of 3 different fairness criteria. And in doing so, we discovered that fairness criteria may actually cause harm to the groups that they intended to protect. So, so before I go into the results, let's first set up the problem with some key definitions. So formally, what is a score? I already mentioned score just now, and formally it is a scalar random variable that is a function of an individual's features. So we can simply think of this as a score as coming out from a black box machine learning algorithm that takes in features and spits out a scalar. And that we already had in our running example of credit. The example of a score is a credit score used in the US to assess credit worthiness, and it's an integer valued random variable. And it might take in, it could be a function of features such as an individual's credit history or their demographic information. So if an individual has a particular score, then a group of individuals will have a distribution over scores. So it might look something like this, which I showed you just now, a histogram. And so intuitively, the score should correspond to an individual's success probability. So in the credit example, this probability would be one's probability of successfully repaying the loan. So to formalize this, we we write down the monotonicity assumption, which states that the score must satisfy this assumption that higher scores means more likely to repay. So now that we have these scores, what can the institution, such as the bank, do with it? So the bank will want to classify individuals using this score. And so specifically, that means choosing an acceptance threshold score that maximizes their expected utility. So what is this utility? For the bank, it would be their expected profit. It consists of two terms. One is the expected reward from people who repay, and subtract the expected loss from people who default. These expectations are taken over the random events of repayment versus default, and also over the individuals in the population. So, for example, we have like a group, like a score distribution that I'm showing you right here. Choosing a threshold score T corresponds to accepting a beta fraction of that group. So you can see that for any group distribution, the threshold T corresponds to a beta, which is the proportion of people accepted. So when there are multiple groups, these thresholds can also be group dependent. So it doesn't have to be the same threshold. And in fact, this is a necessity under certain fairness constraints that we might apply. So now we are ready to define what is delayed impact. So as we saw just now in that example, the scores of accepted individuals will change according to their success. So if someone repays their loan, the scores increase, and if they default on their loans, the scores decrease. So there will be some change at the individual level. And at the group level, that means your distribution of scores in that group will also change as a result. So what is a natural way to model, to summarize this change in the distribution of scores? We can use the mean change in score. And here we focus on this quantity called the delayed impact, the mean change in score in each group. And we denote this as delta mu. It's just the expected difference between the new score and the old score in a group. So let's go into our first result, which is that under very mild assumptions, we can characterize the delayed impact, which is delta mu, as a concave function of the acceptance rate. So if we plot out this curve, it looks something like this. It has a unique maximum. And if we look at what's happening on the x-axis, that's telling us what is the fraction of people in a group that the bank is giving out loans to. So the bank could could have an acceptance rate of 1. That means that give out loans to everyone, which does not sound like such a good idea. Or it could give out loans to no one at all, which is also not a great idea. Because in this case, there is effectively no bank and there is no effect on the average score in that group. And you have a delta mu of 0. So the natural strategy now would be for the bank to maximize their own expected utility. And that results in an acceptance rate of beta max util. And so now here, if the bank actually loans out less than beta max util, that gives rise to average score change that is less positive than under maximum utility. And we call this regime relative harm because the group is, the score is increasing less than under just max util. And because defaults are so much more costly for the bank tends to be conservative. So under utility maximization, it would actually not give out loans to some people who are still likely to repay. So by sacrificing some expected profit and giving out more loans to these people who are still likely to repay can actually increase the average score further. So as we increase the acceptance rate, now we can increase delta mu further up to the maximum of this curve, which is achieved at the philanthropic optimal acceptance rate, is what we call this optimum here. And in this regime, we have relative improvement because the group score is increasing more than under just utility maximization. So now after this point, the bank will have to start giving out loans to people who are less likely to repay on average. So that, again, brings down the delta mu. And if we do this up to a point, then we are again in the relative harm regime, where where the people who default kind of outweighs the people who repay, and then that brings down the average score change, and you're doing worse than under utility maximization. And eventually, if you start giving out even more of these bad loans, then it causes a negative mean score change, and we call this the active harm regime because that actually brings down the group score on average. So what I've shown you here is there are 3 regimes of interest on this outcome curve, right? The relative improvement, relative harm, and active harm. So now the question is, where would fairness criteria put us on this outcome curve, and in what cases does that happen? So before that, I'll first review what are these fairness constraints. So as an alternative to just maximizing the expected utility, we can also maximize the utility subject to certain constraints. So what we saw just now, demographic parity, the constraint is for both groups to have, or for all the groups to have equal acceptance rates. So to just illustrate this with 2 groups, we look at basically, so the dots, all the dots in the group, so include people who would repay and people who would not repay, and we equalize the fraction of people we accept in both groups. So another common fairness criteria would be equal opportunity, and the difference is now we only look at the solid dots, so only the people who would repay, and we equalize the fraction of solid dots that we accept. So this is called equal true positive rates because a solid dot that's also accepted is considered true positive. So now, where does fairness criteria put us on the outcome curve? So the first result is that these 2 fairness criteria I showed you just now, they can actually cause any of the 3 regimes of interest that I described on the outcome curve. And in contrast, so unconstrained utility maximization does not cause active harm. So what this is saying is that depending on the setting, depending on the distribution of scores and the relative group sizes, fairness criteria can put us anywhere on this x-axis. And because the bank is conservative, because institutions are conservative, the utility maximization will never put us in the active harm regime. Okay, so now is there some way we can also compare the 2 fairness criteria and see if they behave differently? So the answer is also yes. So in theorem 2, there exists a class of settings where demographic parity may cause active or relative harm by over-accepting, whereas equal opportunity does not. So what it looks like on this outcome curve is that demographic parity puts us in the active harm regime because it over-accepts relative to the beta naught, which is the threshold for active harm. And equal opportunity does not do that, and in this case gives us relative improvement of the average score. And on the other hand, there are also another class of settings where equal opportunity may cause relative harm by under-accepting. So on the outcome curve, equal opportunity would under-accept relative to beta max util, and demographic parity does not under-accept, and in this case, gives us relative improvement. So what we discover here is that the choice of fairness criteria really makes a difference to the kind of outcome that we see in a group. And depending on which fairness criteria we choose, we could observe completely different outcome regimes. So now that I've shown you some theoretical results, let's look at how we would apply the outcome curve framework to real data. So we looked at 300,000 credit scores. And as I mentioned just now, these scores predict default risk. And so we use these data to estimate the group score distributions, repayment probabilities, and the relative sizes for 2 different race groups, so white group and black group. And if we recall, the main assumption we have to make about scores is that the repayment probability is monotonic in the score. And this is approximately satisfied by the real data, as we can see in this graph here. So other than what we can estimate from the data, we also have to make some modeling assumptions, such as the bank's profit versus loss ratio, which is not something we can estimate from this data set. So we also have same for the delayed impact, which is how people's scores change depending on whether they default or repay. So we pick these numbers to be in a reasonable regime where the defaults are indeed more costly than the repayments are profitable, and particularly more costly for the bank. So with these, we can compute the outcome curves and analyze the delayed impact under different fairness criteria. So if we just plot out the empirical outcome curves for the two groups, it looks something like this. They're approximately concave because our monotonicity assumptions approximately satisfied. And you can already see that these two outcome curves for the two groups are very different because the score distributions are different. So let's look at what happens under utility maximization. So now the bank would pick an acceptance rate for both groups that maximizes its own utility. And in this case, it gives us positive score change in both groups, as we might expect. But if we apply a fairness criteria, now say demographic parity, we find that actually gives us, lands the black group in the active harm regime. So their score decreases on average if we apply demographic parity. And if we use a different fairness criteria, equal opportunity, the black group experiences improvement. And we can also see that in the white group, no matter which criteria we choose, they're all, the score change is always positive. So this corroborates one of our theorems, theorem 2. So we're in the setting where demographic parity is over-accepting relative to equal opportunity. And we can also use these outcome curves and utility curves to get an idea of why the minority group here experiences disproportionately different delayed impact under fairness criteria. So we can see here that the maxima of the outcome curve, the black group, and their utility curves under fairness criteria are very misaligned. So there is, it can experience a quantitatively very different delayed impact when we change the fairness criteria, whereas the majority group does not experience that as much. Yeah, so we can really see how the minority group is very much affected by our choice of fairness criteria. So now that I've shown you some experiments of how we would apply the outcome curve in the real data, with real data, and I've also shown you that our theoretical insights are corroborated by these numerical experiments. So let me just recap what I've told you about our work. So first, we have shared with you this outcome curve framework, which is a very general way for us to deviate from unconstrained maximum utility strategy while improving outcomes. So we're able to use this outcome curve to compare different fairness criteria and anticipate their potential negative impact. And secondly, this is very strong motivation for us to develop these domain-specific models of delayed impact. So if we did not pay attention to the context of the application, just blindly applying fairness criteria could have unintended effects, as we saw in all the previous examples. And now there are many great questions for future work. So in our work, we considered binary decisions, which is just for the bank to either accept or reject identical loan applications. But could we extend our results to richer decision spaces, such as different loan sizes and different interest rates? And how might we do that? And then a second direction is that in our work, we considered the mean score as a way to summarize the change in distribution. But obviously, the mean score is an imperfect way to characterize welfare for a whole population. So another great question is, what other notions of delayed impact could we and should we be tracking? And so finally, our work is just one of the many recent works that have tried to study the dynamics of the impacts that machine learning have on the distribution of variables of interest. So in this case, a welfare indicator. So it's very exciting that our community has started to think more about the dynamics of this distributional impact and how we can take into account the feedback loops in this dynamic setting in order to design algorithms to have positive societal impact. And we think there are many fascinating questions in this space. So with that, I'd like to thank you. And once again, this is joint work with my co-authors. And we have a poster today in here. Yeah, thank you.
Are there questions? Yes?
Yeah, thank you for a very nice talk. Just to make sure I take the right take-home message out of this, it seems your results imply that the fairest thing we can do right now is utility maximization. That is, of course, something that banks, for example, would love to hear. Is that really what we should take away from this, or are there better things that you think are on the horizon that we should be doing?
Okay, okay, thank you for the question. So we're definitely not saying that utility maximization is the best that you can do. So if we look at the outcome curve, utility maximization for the bank does not coincide with the maxima for the delayed impact. So we're already saying that there's a lot of space for you to improve the delayed impact beyond just utility maximization. So the problem is, which part of the curve do we land in when we try to intervene? So obviously, we're not saying no intervention is the best intervention. We're saying there are many ways to intervene, and how do we intervene in a smart way if we care about how people are impacted? So does that answer your question?
Yeah, thank you.
Yeah, thank you.
Can you hear me? Thanks. Okay, thank you very much for your work, and thank you for working on the dynamics of welfare here. What I would argue is that the dynamics are actually even more complex, because it might be that if I have a higher acceptance rate, then this increases the probability of paying your money back, because you inject more money into the community, and thus it might be that more people are actually able to pay their loans back. So in that case, it might be better to have a higher acceptance rate, right?
Yeah, I thank you for the question. I think that is a great point. So that's also something we've considered when we think about like multi-step effects. So I think there's definitely something more subtle that goes on when you consider how you would inject like more like money into the community. So it is something that we've thought about, but it's not something that it was the scope of this work. And great to talk about it more offline. Yeah, thank you. Next question.
You hear me? Okay, hi. Yeah, thank you for the talk. So I sort of have a comment that is sort of a question. It's that it seems slightly convoluted to me in your example that you define harm to be a negative effect on credit score, when sort of the result of that negative credit score is simply going to be that they can no longer get loans in the future. And so it seems weird to me that the solution to this would be to accept fewer people for getting loans in the first place. Did that make sense?
Yeah, sure. So to make sure I understand what you're saying that if you don't give loans, you have no effect on people who have lower credit scores?
Yeah.
Is that what you're saying? So yeah, so clearly our model is sort of like a simplified model of the real world. So in the real world, there might be many sort of drift effects for how people's credit scores would change. And so we are only, obviously we cannot model everything. So we're just trying to say like, okay, if this is the only way scores can change in this model, then we can characterize some very clear effects of over-loaning and over-accepting. So once you want to take into account what are the other ways of improving people's credit scores and abilities to repay, I'm sure there are other dynamic effects that we have to take into account in a model. So
okay.
Does that make sense?
Yeah. So I guess just a slight follow-up is, do you have any examples of other sort of metrics, other scenarios where you have this delayed impact other than this credit score?
Yeah, so I would definitely like to draw attention to some other works in the community. So these references here, we have, so they have different ways of looking at dynamic impact. And I would definitely encourage you to talk to these authors to look at the other ways they are modeling the delayed impact.
Okay, thank you.
Yeah.
So we'll just take 2 more questions, and then we'll take things offline. So
Thanks for the exciting work and fantastic talk. I was curious, when you start this estimate, you need to have an unbiased estimator of the score for a particular population. And I was wondering if you could comment on if that initial assumption is violated. So if your initial estimates of this probability of repayment is biased in some way, how that would affect the model and the dynamics that you describe here.
Yes, thanks, Katja, for the question. So that's a great question. So in the paper, we actually also consider a case where there is some bias in the score. So we call that measurement error. So it's in a case where the group's credit scores are systematically underestimated. And you find that in that situation, it actually expands the regime where applying a fairness criteria such as demographic parity would give us a positive impact. So yeah, I would definitely encourage you to look at the full version of the paper, and that's a great question because here we are only covering the sort of the situation where bias is not such a big problem. But thank you.
Hi, a quick question on the empirical study, and I think the question is probably related to the previous one, which is if you look at the score distribution of the two demographic groups you have, there's a gap. And I think of these scores, bank loan repayment is a primary drive behind the development of these scores. Do you have any comment on whether this gap should exist and why it exists? This is the gap.
So yeah, this is the gap you're talking about, right? Okay, yeah. I guess I'm not able to comment on why exactly FICO credit scores have this gap. So if I understand correctly, I think because we sort of assume this monotonicity assumption, and if we kind of transform the mapping, we're able to make the gap disappear, at least for our empirical simulations. So I'm not sure if I'm answering your question, but maybe we can talk more offline if it is about how we did the simulation.
No, it's actually not about how you did the simulation. Okay. I'm simply making the observation is that if the score is supposed to denote, I think by and large, delinquency rate, then we really shouldn't be seeing this difference between different demographic groups, right? Yeah. And I think in your answer to the previous question, it indicates the bigger this disparity between the original distribution, the bigger I think these fairness criteria will have an impact when you add that to the acceptance rate consideration. So the question really is, did you have any thoughts about this gap when you see it in the data?
Yeah, I think part of this problem is the score is a black box, so we sort of don't know where it comes from, and then all we observe is that there is this gap that shouldn't be there in an ideal world where we really know everything and about the scores. So I'm happy to take this discussion offline because there's a rich literature about things like calibration, like the same score mean the same thing for different groups, and I think that's definitely a question of active research.
Thank you.
Thank you.
So let's thank the speaker again, and you can have your questions offline and the poster session too.